Okay, so welcome. Thanks all for attending. We don't have exactly a chair, so I'm just gonna give you a very short introductory words. Thank you all for attending this panel. Sorry, I hate this mic. So, we'll go in the order of the program. So we're starting with me, and I think the one after is you, Robin, yeah, right. And then it's Cascade, and then Chengwei, yeah. So yeah, I'll be starting. Thanks everyone for being here today. I'll be presenting what really is ongoing work, and actually even early ongoing work as part of a project that is funded by the Department of Defense Minerva initiative. We are trying to set up a model of migration flows out of Central America and West Africa. This is specifically meant to be a predictive model of migrations or at short time scales. And this is done collaborative with colleagues at Columbia University and Oregon State University. You can see them, they're all listed there. Couple of words more. The overall project where we are, what we try to do is compare and better understand what explains the recent rise and changing characteristics of migrations in both Central America and West Africa, specifically related to the rise in unaccompanied minors out of both regions into the EU and the US. As part of this project, we also will soon run a Twitter random survey to better understand how migrants make decisions and what are the reasons that are self-reported reasons that are motivating the migration decisions, as well as we'll also have or aim to have some field research in Honduras and probably Gambia. But this is kind of a side project I'll be presenting today, where what we really want to do is building a predictive model of migration in both out of both regions and compare the drivers in both regions and how they leads to migration response. How does this work? Yeah. So maybe with a delay. So a couple of words on motivation. We now have a burgeoning literature that looks at long-term migration projections. Probably the most well-known is the Groundswell report that have been published, that have been collated by Rigaud and the Sherbinin, published a few years ago. There's been a number of follow-up projects. I've been involved in the most recent one, the African Climate Mobility Initiatives, that was just published this year. And there has been a number of other attempts, including by Ricani and Choué at building model that aims to explain long-term change in migration flows, focusing on climate change and socio-economic pathways. Now, these models are very long-term. They typically predict migration out of at least a horizon of 30 years. And they rather probably better described as projection rather than predictions. But so far there's been very little attempt at building a short-term predictive model of migration in the literature. It's been a couple of attempts by statistical offices. I think Sweden has one, for instance, but that's kind of the exception. And this is a bit surprising because in other areas, for instance, for armed conflict, we do have predictive model of conflict, for instance, that has been developed over the past few years. So this is something we want to do here. Next to this, we have actually a large literature that aims at causal identification. So how a given factor influence migration in this case. The premise that's the very narrow focus of these studies makes it a limited platform to understand and model how migration might change across a wide range of different factors over the short term. So here we attempt to fill this gap and build a predictive model of migration separately for both Central America and West Africa, but with broadly speaking, same type of predictors in both regions. We integrate a range. We aim to integrate in the data gathering process. At this stage, we aim to integrate a broad range of different factors, social, economic, political, as well as environmental driver of migration. I'll come back to this in a minute. Yeah, as I mentioned, we'd like to better understand how different drivers may lead to different response across region, and understand how this also, but specifically in the case of Central America, because we are more disaggregated data, understand how this might also affect the change in the composition of those flows, especially related to unaccompanied minors. Couple of words about our general approach. So we use data on irregular migrations. So this is a form of migration that is politically silent, as you all were well aware. It has led to significant backlash in recent years, both in Europe and in the US. In the case of the US, we focus on operation at US southern border from fiscal year 2010 so far. We use data by the Border Patrol. These are actually individual records of migrants that have been apprehended at the US southern border. So we have about 6.5 million individual records of apprehensions. And we're trying now also, this data have been obtained by colleagues at University of Virginia for a freedom of information request, and we're trying now to expand this data back in the 90s for a separate freedom of information request. Separately, we have data on irregular migration, on detection of irregular migration actually from the European Union. It's been assembled by Frontex. This is the EU border agency. And this goes back to 2009, but this is a hard limit. There's no data before this. We want to develop a model of prediction that is kind of similar to what some of you might be familiar, the VIEWS project on predicting conflict at Uppsala and Prio in Norway and Sweden. Maybe a slight variation we'll be using here Bayesian hierarchical model and do this separately for both West Africa and Central America. So how and what is those data we plan to use? So here I'll show you a graph by Frontex about the flow of migration across different routes to Europe. What you can see is that Frontex assembled data across a number of different routes, from the eastern borders to the eastern Mediterranean route across Turkey and the Aegean Sea to a number of routes across southern and western Mediterranean Sea and to Western Atlantic routes to the Canary Islands, as well as two internal routes. In our project, and this is a snapshot for 2018. So do not assume these figures are representative of the flows at any point in time. They change actually quite a bit from time to time. But in our case, we focus really on those three southern Mediterranean routes, for which most of the migrants out of West Africa actually transit through. So that's the Central Mediterranean route to Italy, the Western Mediterranean route to Spain, as well as the Western African route to the Canary Islands, which has become increasingly important in recent years for reasons I'll come back to this a bit later. Where do migrants from West Africa originate? So this is a plot that shows you a map, actually, that shows you total out migrations of irregular migrants since 2009. The primary sending country is Nigeria, owing to the fact it's the largest country in the region. Nigeria is, there's a fair margin between Nigeria and the nearest country, which I think is Guinea and Cote d'Ivoire, if I'm correct. Nigeria is one of the top 8 global sending countries to Europe, and it's the only one with Eritrea, which is above 100,000 in our sample. This is a bit underestimated, of course, because we only see those that are detected, but it gives you some insight. Other than this, most of the migrant origins in West Africa from the countries located along the Gulf of Guinea or the Atlantic, except with Mali, which is a specific case because of the civil war in recent years. Silent countries and much lower number of migrants. And in fact, if you had like disaggregated data, you could even see that in Nigeria, most of the migrant originated from the south and southeast region of Nigeria. Now, this picture is a bit misleading. It's important to keep this in mind. If we do the same plot, but like look at the rates relative to the total population, Nigeria is one of the countries that send the least migrants. Most of the migrants on a relative basis comes out of Guinea here and Gambia. Gambia is the primary hotspot in terms of relative to the population. So that's always something to keep in mind. What about the trends in our data? We see overall like a secular increase in the number of migrants up to about 2016, 2017. It peaks about a little after the 2015 refugee crisis in Europe. And then there's a marked decrease. What does explain this marked decrease? It actually relates to increased enforcement first along the central Mediterranean routes toward Italy, starting in 2016 onward. We see a marked decrease. It's then a rebound a little bit because it's important to keep in mind those migration routes. They respond to each other. So as the central Mediterranean migration route is closed, most of the migrants reroute themselves toward Western African migration, Western Mediterranean route towards Spain, for instance. And then later, this one is also under increased enforcement pressure, and we see more migration going toward another road, and particularly the roads to across the Atlantic to the Canary Islands. But overall numbers are down compared to what they were in the peak in 2016 about. This is the somewhat same data on US apprehensions at the southern borders. You may be more familiar with this data, so I won't speak too long about it. But it's important to keep in mind most of the migrants enter the US in Texas, New Mexico, Arizona to a large extent. And there's multiple roads, of course, but like the main difference is, of course, that those routes travel for a single country, which is in this case, Mexico. What about like the numbers? Here, the primary sending countries over the period is, of course, Mexico, owing to historical ties between US and Mexico, as well as its proximity. One interesting thing, we have an important increase in the number of migrants from 3 countries in Central America. And I think that's something we really want to focus on. It's Guatemala, Honduras, and El Salvador, which have become primary sending countries during this period. Overall, we have about 5.5 million migrants originating from the Central Americas over this period, of whom about 1 million come from those 3 countries. Over 1 million, sorry. Again, this is the trend in the data. And what's interesting, we see actually, this is a log scale, so keep in mind, small difference makes actually large difference. But we see a secular decrease in the number of migrants out of Mexico during this period, and a concomitant significant increase in the number of migrants from those 3 countries I just mentioned, Honduras, Guatemala, and El Salvador. They actually catch up from about 2016 with the number of migrants out of Mexico. And if you're interested, this sharp decrease here is related to increased enforcement and limitation of migration through Mexico by the Mexican government under pressure from the Trump administration at this time. Good. So just something to keep in mind, whenever you try to model across different regions, the data is not exactly the same. US Border Patrol formally measure apprehension of deportable migrants between border crossing point, and these are actually collected by a single agency, US Border Patrol. And the nice thing about it is you use common definition and common reporting system. So the data there is substantially similar. The problem with the Frontex data is actually Frontex is a relatively weak agency, although there's a lot of like public interest in Frontex, a lot of criticism. Frontex is just a weak coordinating agency at the EU level. The border enforcement is being done by border agencies of EU countries, and they may use different definition. They may use have different level of border enforcement, so the rates of detection might vary from country to country. And as we saw sometimes, and most tragically the previous week, some countries also do not want necessarily to register those migrants in the hope that they would then travel later forward into deeper into the EU. And that's why we saw last week when about 700 migrant drone off the coast of Greece, the Greece Coast Guard were trying to get them into Greece, and that didn't quite work. So how do we go about? So we will be using Bayesian hierarchical models and accounting for a number of factors. I'll come back to this. The advantage of Bayesian approaches is that they're really flexible. First, we can account for unit or panel heterogeneity. So how, like, for instance, the effect of climate could vary from country to country, right? And Bayesian hierarchical models allows you to leverage information within panels in a weighted average approach, and allows you to have more flexible estimates that might account for the fact that you may have less exposure to climate shocks in some country, or more adaptation capacity. Another aspect of Bayesian models, they're very flexible, so we can have different functional forms, and that matters since we use count models, and some of those count can be zero in any month or year. Our primary unit of analysis is the country of origin year, but we hope to shift in a later stage to a monthly resolution. And we'll do so separately for West Africa and Central America. Just a little bit about our workflow before going over the predictor and ending there. So we'll be estimating multiple models using different set of predictors and different functional forms. We then assess the predictive skills of those models using posterior predictive checks. And the idea there is that you take your estimates of your model, you simulate new data set, and you look at some feature of interest here, for instance, the mean number of migrants, and you look at how this compare across your maybe 100 simulated data set to your observation. So these are a histogram of mean here in panel A. Of your simulated data set, and we can see this model is actually performing really badly because the observed mean number of migrants is very far from this histogram. And model C here is already a bit better. We're still far from ideal point, but it's still already performing better. So posterior predictive checks allows you to focus on aspect of your model, assess your predictive skill of a model related to aspect you care about. And then we also use a more formal way of doing it using Livelihoods cross validations, which give you goodness of fit statistic that allows you to perform in a subsequent stage model selections. We also use a benchmarking using clustering approach and machine learning technique. I won't be using this, it's a bit outside of my area of expertise, but my colleague will do this. And hopefully at some stage we have some projection and we'll set up some scenario to project how migration might evolve in the future. We have a different, I'll finish on that. We'll have a different set of predictors. As I mentioned, we'll estimate these models separately for each set of predictors and then jointly together and look at how these contribute to the model fit. We have a baseline model with just population distance, and then we'll look at some economic indicators. GDP per capita, youth pulse, as well as the composite indicators of price level to account for the fact that most of those countries are rural and therefore price variation in price of crops may matter for household livelihoods. We look at social drivers of migration, mostly migration network measures, so past migration, diaspora destinations, institutional aspect. We'll also look at COVID, of course, since this period will overlap the pandemic. And in the case of West Africa, we add some measure of political violence. These are key drivers in the region, and in Central America, homicide rates, of course. In terms of environmental drivers, we'll be looking at composite indicator of precipitations, vapor pressure deficit, and killing degrees across crop growing area and season. This will be again a weighted indicators. And in West Africa, we aim to also look at fishing stock because that's often been mentioned. Depleting fishing stock has been mentioned as a driver of migration to regions. In the case of West Africa, we also look at condition in transit countries in North Africa again, because some migrants might, maybe experiencing may stay depending on the economic conditions in Morocco or Algeria, for instance. And finally, a destination we will focusing here there on border enforcement measures, right? And yeah, as I said, this is still very early stage, so this was mostly a conceptual presentation. We were hoping to get some initial results, but it took us more time than we expected to get there. So thanks again for your attention, and I think I'm running out of time. So.
Okay. Wow, that was a lot of information. Thank you, Fabien. My name is Fabien van Duijne. I'm originally from the Netherlands. I just joined the climate school. I'm a postdoc here, and I work with the research group CIESIN together also with Fabien. My project is called On the Move Towards Fine-Scale Climate Migration Modeling in India. It's working. Yes, we got it. Okay, so This session is called Modeling and Visualizing Climate Mobility and Managed Retreat. I will not talk about managed retreat, but I want to talk about how to model and visualize climate mobility. And I'll try to slow it down. If something is unclear, I think it's also fine if you can ask a quick question. I am very, very critical of modeling approaches. So that's why I want to start with why are better modeling approaches necessary? I want to then introduce my own study, which is an exploratory study in its incipient stages. I then move on to what I call a conceptual contextual framework in 10 bullet points. I'll run through these really quickly. Then I'll present my study design on how I think we can make approaches in climate migration modeling. And I will close off with some findings and discoveries on where I am today. And then with some questions, not necessarily from you to me, but from me to you. So pay attention. Okay. Why are better modeling approaches necessary? Like I said, I'm very critical of these modeling approaches. There's a professor walking around at Columbia. His name is Upmanulal, and he reviewed 120 papers on climate migration modeling. And he said he couldn't find a single one that didn't have some inherent problem, either in its assumptions, in its parameters, in its R-square, using the wrong regression model for the wrong type of data, et cetera, et cetera. That is very important. I also think that another problem with this literature is it's interdisciplinary, and it's to an extent that it becomes problematic. So to really understand this, you need geographers, anthropologists, you need migration scholars, you need people who work in hydrology, who understand the water cycle, you need people who do agronomy, who are into crop modeling, of course, climatology. You need statisticians and data scientists. And usually there's one person who tries to do everything, and that never works out. And this is for me the most problematic point. The dependent variable, so the one that everyone's trying to predict, has been active for a long time. People have been migrating all over the planet for forever. And also climate has been there for forever, right? So there's been floods, droughts, so you're trying to model, you're trying to isolate a climate change effect on a dependent variable that has been active forever. So that's very problematic, right? And a lot of people have written about this. For instance, Hein de Haas, he's very critical of this literature. Also, François Gémen and Ingrid was. Okay, let's just move on. I'm very critical of this literature. Okay, you get the point. So my research question is, how can we improve these modeling approaches to better understand the strength of the linkages between climate change impacts and these human mobility flows? My geographical focus is on India, and I also have the feeling that I'm one of the very few who does India. I understand why there's a lot of focus on Central America. I understand why there's a lot of focus on Africa. If you want to get funding from Europe, you focus on Africa. If you want to get funding in the US, you focus on, but in India, not necessarily. So I'm doing India. Why? India is now the most populous country on the planet, 1.5 billion. 1,500 million people, that's a lot of people. Largest agrarian population on the planet, 700 million people work in agriculture or are dependent, I said that wrong. They are dependent for their livelihood in one way or another on agriculture. And this is spread out over around 650,000 rural villages. It is also the largest vulnerable population to climate change impacts because these are land-based livelihoods. As I said, this is understudied, under-theorized, data-scarce environment. There is no systematic data on migration, let alone labor migration or seasonal migration from India. And it's incredibly complex, for instance, because there are all kinds of caste dynamics and class dynamics and religious dynamics. So very poorly understood. No pressure, but then let's try to make sense of this. Okay, this one is very obvious, so I'll present 10 bullet points. I'll run through them quickly, and then I'll turn to some maps, and then you get excited again. Migration decision, everyone knows this, but I have the feeling that I should reiterate. Migration decisions are influenced by a mix of socioeconomic, cultural, political, and climate factors, and it is very, very difficult to isolate that last one from the rest, if not empirically impossible. Okay. Let's try it anyway. In India, the agrarian pathway to climate mobility or climate migration is the most important one. Like I said, 700 million people are dependent on agriculture, and climate change is putting mounting pressure on these agrarian livelihoods. Again, very important. Anyone who's ever traveled across rural India, there are no or very few alternative livelihoods in the countryside. Even so, we do not anticipate large-scale, permanent rural to urban migration. People are very strongly tied to their places because of very strong caste ties, sub-caste ties, religious, community bonds to the village, emotional and ancestral bonds, shared family homes, shared family land, rural identities. People do not necessarily want to permanently relocate. India is not exceptional in that sense. This happens all over the planet. Okay, so again, to reiterate, we have a large population. Climate change is putting mounting pressure on their livelihoods. There's no alternative in the countryside. They do not want to move, but they also cannot move. There's a big literature on exclusionary urbanization. India's overburdened cities are becoming increasingly unwelcoming to the rural poor. Okay. What then happens? It's internal temporary male labor migration that serves the needs of the household best. Again, not something like brilliant that I came up with, but this is the pathway that we are seeing in India. And there's no data on this at all. Most people were super surprised when COVID happened and suddenly all the states closed their borders and wow, there's a lot of yeah, I know that was pretty crazy. This is also the propensity to migrate strongly contingent on caste, class, religion, whether or not the household has land, gender composition, etc., etc. There's a large literature on this from anthropology. Point 7, I'm almost done. This is also very important. Not many people notice, but the cropping patterns in India, I'm turning to agronomy now. Cropping patterns in India are very, very specific. So you have certain regions where they grow bajra, certain regions where they grow soy, certain regions where they grow maize. And all these crops respond differently to different climatic stresses. It's not necessarily linear that all crops experience the same agrarian distress during a drought. Some crops actually do much better under certain climatic conditions. Point 8. So this necessitates a much deeper understanding of agronomy in India, right? Where you have different growing seasons with different crops that respond differently to different hydrometeorological stressors. And there are all kinds of mitigation strategies nowadays. So farming communities are becoming more resilient. They're using more drought-resilient crops. And that is all putting pressure on this presumed causal relation between climate change impacts, agrarian distress, and labor migration flows. Okay, the last one. It's also not a linear trajectory. So you see high dynamism in rural India. Households can resort to labor migration one season and then resort back to a more land-based livelihood. And that is so it's very difficult to model that. And still, usually what we're doing, we have a population, we have a climate risk, they're all going to move. That is ridiculous, in my opinion. Okay, now, how am I going to study this? So how does a conceptual model like that translate into a research design? I always urge for sort of a research design that looks at these issues from above and from below, merging high resolution climate data with social science data from above, so you could start to understand patterning and then also conduct thorough field work. Systematic primary data collection across diverse localities in the field. So what I did, how are we doing on time? I'm just rambling here. Oh, we're good. Okay, so 8 different data sets I'm merging. Most importantly is that we now have the major crop grown in each and every individual Indian village. We have that for all 650,000 villages. We also know the exact agricultural workforce across the censuses. So we know exactly how many people worked in agriculture, how many people moved in and out of agriculture between the census years. And we've managed to connect all of that to the correct village boundaries. So then we can look at the spatial patterning, right? For the natural science data sets, we rely on precipitation and temperature data from the Climate Hazard Center, which now provides very fine scaled at a 5 by 5 kilometer grid cell precipitation data. So basically what this means that for each and every individual Indian village, we know every day how much rainfall that was, what the maximum temperature was, what the minimum temperature, what the average temperature was. That is a ridiculous amount of good data. And then we can start to integrate future climate projections in there as well. With the overarching purpose, right, to understand, are people moving out of agriculture because of certain climatic conditions, knowing that there are no alternative livelihoods that people will then start to migrate. That makes sense? Yeah, okay, great. The next step, this is from below part. This always has to be validated in the field. So we're planning on conducting about 2,000 household surveys across different locations to better understand these intricate dynamics. Who migrates? Is it in fact true that there are no regional or local jobs? Why do certain households migrate and why do others not? Okay, first discoveries after brutal data cleaning of the Indian census, which is horrible. That took me a long time. Okay, yeah. After this comes a map. You're going to be thrilled. Okay, so I excluded all the disputed areas because that's just messy. Then the uninhabited villages, the islands, and villages where no agriculture takes place at all. That drops about 75,000 villages. So, but we are able to get workforce data on almost 600,000 villages. Of those, we see that a structural shift away from agriculture takes place in 300,000. In 300,000 villages, we see that people are moving away from agriculture, and that happens mostly in the states of Jharkhand, Western Bihar, Eastern Uttar Pradesh, and parts of Rajasthan. However, there are about 250,000 villages where we see an increase in agriculture, right? So I'm thinking of a magnificent paper called India's Great Agrarian Labor Reshuffle. But what is the influence of climate change on this? This is a very bad map, but I had very little time. So this is the male workforce analysis, and I'm only looking at males because males migrate, females do not. Movement away from agriculture at the village level. Again, it's a very bad map, but you can sort of start to see that there's a cluster emerging here in Bihar and Jharkhand, but not, also here in sort of the eastern part of Rajasthan, but not necessarily in central India, in Madhya Pradesh. If we zoom in on that a little bit, again, very messy, but I got a thingy. Oh, that doesn't work on red. But this is Jharkhand, northern part of Jharkhand, that shows very strong movement away from agriculture, and this is the eastern part of the western part of Bihar that also shows very strong movement away from agriculture. And then Madhya Pradesh, no. Okay, so that raises a question, why? Okay, so we start to look at crop patterns, and then we see that in those areas that show high outflow, and there are tons of other reasons, but at least this was also some of the things that came out of the analysis. Rice is the main crop in those regions of Bihar and Jharkhand, and the cropping patterns in India are magnificently geographically bounded. So soy is only grown here in central India, in Madhya Pradesh, and soy is doing better under certain climatic conditions, which is why we do not necessarily see movement away from agriculture. This is bajra. It's also a main crop, but predominantly in Rajasthan. And we can see that is even grown on the edge of the Thar Desert. That is a very drought resilient crop, but still under certain, because that area is hit pretty hard by certain climatic changes. There we see movement out of agriculture. What else do we have? So this is I'm very proud of this. This is a standardized precipitation and evapotranspiration index. Some people will be familiar with it. Technically, it's not so fancy, but this is at a 5 by 5 kilometer grid cell. So again, we know for each and every Indian village now if they experience drought or not. This was a image taken, what is it? June 2009, which was a horrible year. So this technically, the monsoon should have had arrived, which it didn't. So you can see areas going into orange and red zones. This is July, still monsoon didn't arrive. And now we can see the entire Indo-Gangetic plain light up. This is an area where 400 million people live and crops are failing. 2009 was a very bad year. And this was then in August. And now the monsoon starts to arrive, but still large areas experience drought conditions. Okay, I'm going to close off here. The key point, and again, so we're just starting off this project. We are looking for the spatial and temporal correlations between the structural workforce shifts away from agriculture and these certain hydrometeorological stress moments. We control for the crop, we control for the season. We also have irrigation data at the village level, which we can control for, and that we'll be using to understand this problem a little bit better. I want to close off with questions. Okay, what do you think of this conceptualization? What do you think of the assumptions at the base of this conceptualization? So I'm not assuming that I'm right here. I fully acknowledge that I could very well be wrong. Is there something missing? And now I want to make a bridge to your presentation, because you asked me to look at a data set. Well, you didn't, but I looked at it. And this is a data set from, this shows dangerous, hot, humid days. It's a global data set using temperature data and humidity data, and using a threshold at 32 degrees. Basically, this shows the entire Indo-Gangetic plain lighting up. Which means that every year that part of the world is experiencing 2 more of these days, and then consider that everyone in that area is reliant on agriculture for their livelihoods. So doing hard manual labor. There's small farmers. There's not much automation going on there. And very few people are talking about this. I find it fascinating. So this is, for me, one of the most problematic cases of climate mobility, and I want to leave it there, and then Cascade, you can move on. Thank you.
All right. So the data Robin just put up is totally wrong, and I will own that. It may or may not be wrong. I'm going to talk about that for a second. So yeah, my name is Cascade Tuholske. I'm an assistant professor in the Department of Sciences at Montana State University. Very recently, I was a part of CIESIN and of the merry band of climate mobility specialists. And I'm really excited to be here to actually present my colleague Emily Williams' work at UC Santa Barbara. Actually, I believe Emily just started a new job at UC Merced. And then Chris Funk and Pete Peterson are really kind of the people who spearheaded the initial idea behind developing some new higher resolution projections for climate change. And so, yeah, I just want to really emphasize that all your critiques of this work, please just send them to Emily, because she is the lead author. We'll just click here. Oh, there we go. So just to thank the funders behind this project, as I said, the Climate Hazard Center at UC Santa Barbara is really the lead institution here, and they're supported by the Bill and Melinda Gates Foundation and USAID through FuseNet. My funding comes from the NASA Land Cover and Land Use Change Program, and then institutional funding at Montana State University. So when we think about, if we're going to take a very environmental deterministic framework of climate mobility and habitability, at some point, there are places where humans don't really like to live. We don't really live in Antarctica. We probably will not. The jury is still out on Mars, but I don't really want to live on Mars. So there are some real fundamental physical conditions that as animals, we don't really want to be in. And very generally, this is related to humidity levels and ambient temperatures and what that means for our health and our food systems and our well-being. And so if you think about a location on the planet where the humidity is going down and the temperatures are going up, that generally is thought of in a climate mobility or habitability framework as something that affects our agricultural production, the agricultural pathway that Robin was talking about. And that's, for a smallholder, that's not a good thing. That can decrease local food security, but more importantly, I would say it impacts livelihoods for farmers and pastoralist communities around the world. At the same time, there are pathways, depending on where you're living, where humidity may be increasing at a rate faster than temperatures are increasing in terms of the amount of moisture in the air. Of course, as temperatures go up, the air can hold more moisture, but there's some very good kind of robust literature showing that in some places on the planet, that moisture loading is exceeding the air temperature loading, and the combination of those temperatures reach true physiological thresholds whereby we cook like an egg and we die. And as Robin alluded to, there's fantastic work talking about the implications of hot human heat and labor output. Kyle Ming has a wonderful paper about labor output in China related to temperature change in factories. So it's not just agricultural communities that can be impacted by these extremes. But unfortunately, the historical temperature record and precipitation record is pretty weak. So right now we have, or on the screen, let's see, the Indian subcontinent. The green dots are roughly urban settlements. There are 3,000 of them, in order of magnitude less compared to rural settlements, it sounds like. And if you pull, global standards of station data, there are about 111 weather stations with a reliable reporting record. In fact, in 2016, there were, I think India's on here, India, Ethiopia, and like 4 other countries in August 2016 had no global weather reporting in these official records. That's in 2016. Is that me? I guess I'm getting played off, so I will take my leave. So with this, station data is rare in many of the most populated places on the planet. So really understanding how the climate is changing is hard if we're just using station data. And so Ben Zaitchik at Johns Hopkins University and I wrote this little mini paper where I very roughly calculated how many people live near a weather station with a longitudinal record, and about 4 billion people live more than 25 kilometers away from a weather station. How many of you live in San Francisco? No one? How many of you been to San Francisco? How quickly does the climate change in San Francisco as you walk around the city? Yeah, block and a half, exactly. And so in terms of, and then people move around, so that's another big problem. So Climate Hazard Center at UC Santa Barbara initially thought about this question from a precipitation standpoint, and we've extended this into the temperature space. So if you look at a climate reanalysis product to break this problem up spatially, and I'm going to talk about climate projections in a second, you have a person and you have an Aero5 climate reanalysis product. It's about 25 kilometer grid cell. So if your Aero5 is your baseline, and then you want to talk about projections, this is a 100 kilometer grid cell, which is a very high resolution GCM output. Many of them are 250 kilometers. So to really understand how the climate is changing from a human perspective, or somebody living in a city, this becomes very challenging, or somebody working on 2 hectares or less, which is about 30% of the world's food supply. So, and I'll talk about the methodology in a second, but what we're working towards is taking the CHERTS, which is the temperature record, and the CHIRPS precipitation record to try to take our pink squares and get them down into our blue squares. So we have a much higher resolution understanding of how the climate may change. So again, just to give this context from Los Angeles, when you take a global climate model output at 100 kilometers, you have lovely Santa Monica Mediterranean climate all the way out to the hottest desert on the planet. And that's showing up in one climate model output. So that makes understanding this notion of habitability just from a sheerly environmental deterministic functional standpoint very, very challenging. So the CHERTS and CHIRPS record leverage basically a moving window regression approach that blends station data with satellite data. The process is a little different. The precipitation record uses thermal infrared imagery of actually looking for clouds, because clouds are very cold. They're really easy to pull out from weather satellite archives. Whereas CHERTS relies on thermal infrared and land surface temperature that gets converted into air temperature. And on the temperature side of things is really what I'm going to focus on. We have to first build a background climatology, because it's really, especially for the tropics, you don't get daily cloud-free images ever. And so that initial CHERTS data set is a monthly maximum temperature. That's that blended station satellite output. And then we use those months, the monthly data to bias correct Aero5 down to a daily 5 kilometer temperature record. And what we've done is we've extended this into correcting dew point temperature, or using dew point temperatures to create relative humidity, to estimate vapor pressure deficit, which is really a strong indicator of crop health, and as well as animal health can be used as well. On the agriculture side of things, and then on the human side of things, we're producing daily heat index and wet bulb globe temperature, an approximated wet bulb globe temperature. And one caveat I want to say is if you're constructing a hot, humid heat metric, the sensitivity in the diurnal cycle is very precarious, so to speak. So if you're making heat index, which is what we use in the United States, a little bit of change in moisture at a very high temperature can have a much different output. In fact, if it's 100 degrees out and there's 20% relative humidity, the heat index is lower than the air temperature. That's how sensitive it is. But if you get it up to 30, it's actually much higher than the air temperature using NOAA's equation. So just a caveat that these data sets, especially on that compound hot humid heat metric, are very sensitive. So we're doing our best here, but I want to give that caveat. And then in this paper that Emily just submitted, we validate the observational record. Cherts and chirps have been validated in other papers, but we revalidate them here for just to be thorough. And then we validate with the available station data, our vapor pressure deficits and our average relative humidity. And in this case, average wet bulb globe temperature, even though the data set we build is a maximum wet bulb globe temperature, because the station data tend to not have a whole diurnal cycle for the moisture parameters in the global station record. And in the tropics, we're doing our best, but they're still quite a mess. And I really recommend you read this preprint that Aaron Coughlin de Perez just released, comparing all the different climate reanalysis products against cherts, and basically shows that MERA versus ERA, which are two climate reanalysis products, just with air temperature have different months, 6-month difference in the tropics of which one is the hottest. So when we think about the convoluted process of the decision to migrate as a human being, that's very complex. But the things that I think, as I can be both a social scientist and a physical scientist, so I can make fun of both, but my social scientist friends, we'll take some of these climate model outputs or reanalysis products for what they are and trust them. And the same thing, my physical scientist friends will take, say, a gridded population data set, but know that anytime we mix these two, we're compounding that uncertainty. And we're doing the best we can, but I think acknowledging that and being really forthright with how we're using these data is key, and maybe not fighting with each other as much as we do about the nuances, and just recognize we're really doing the best we can with the limitations when you have 111 weather stations for over 1 billion people. So into the projections. So we take the very short way to do this is we take the temperature of the precipitation record from 1983 to 2016, and we say, that's 365 times 34 days. What would each one of those historical days look like under a 2050 forcing scenario? Or 2030. So we take the CMIT6 model outputs, and we calculate the difference between the observational model or the historical model runs and the future model runs. And we take that delta and then we apply it to the cherts and the chirps record. So our projections for, say, SSP 245 in 2050 is 34 years of data. Again, centering on that delta between the model outputs and the model projections and the model historical runs. And then we use that delta and we perturb it through, in this case, I'm emphasizing the vapor pressure deficit and the wet bulb globe temperature, the maximum, to develop this 34-year projection record. But we also have daily precipitation, minimum maximum temperature, and average relative humidity. And from this, we're able to resolve potential future climates and basically potential future weather scenarios at a really high degree of spatial resolution in a way that I have yet to see been done. And when you're in the business of predicting the future, you're probably pretty wrong, but we're doing what we can. And you can start to understand both that hot, dry change in terms of vapor pressure deficit and the spatial contrast with our hot, wet change. And because we produce daily data, this is just a couple of months, but you can look at seasonal changes. You could pull out El Nino years versus La Nina years. There's a lot of advantage to having that kind of historical temperature fidelity. So I actually, I thought I only had 12 minutes, so I'm going to be ending my slide talk quite a bit early, but I will take questions at the end. But I really want to emphasize things that I've heard throughout this conference so far is that this habitability is very subjective. It depends. When I teach intro to human geography to 200 Montana kids, I always start with Dubai. We can live wherever we want. Elon will send us all to Mars. It's going to be great, I'm telling you. It's really up to us to define what we want to be as habitable. But at the same time, we have to recognize those very inherent structures are not necessarily going away overnight that determine what is habitable and who can live where. And with this, we have to start bringing in a stronger understanding of the limitations of our climate data and try to anticipate what this means for the 4.5 billion people currently living in cities that occupy 3% of the world's land surface area, or the say 600 million to 1 billion smallholder farmers who produce about 30% of our food, and recognizing how spatially heterogeneous those, not just the climates are, but those livelihoods are and what determines those livelihoods. And we're hoping that this data set can really kind of move the needle. And the last thing I'll say, I just got an email from Chris Funk this morning that I don't want to give a timeline, but this whole data set should be operationalized for rapid attribution so that if we make it through peer review and people find this to be worthwhile, that in real time we can start attributing any sort of climate extreme at a much finer spatial scale to climate change versus natural variability. This is the hope with this data set. So thank you so much for your time.
Hey, good afternoon, and thank you all for being here and sticking around to the very end, I guess. So my name is Shengzi Wen. I also go by Jackson, so a bit easier to pronounce. So I am an assistant professor of structural engineering at the University of Colorado in Denver. And my research really focuses on novel and innovative strategies towards climate adaptation. So climate adaptation in general, not just for retreat or for relocation. And I'll be delivering this talk partly on behalf of my colleague, Professor Han, who's also with us today in the audience. So the title is Immersive Virtual Reality as a Communication Tool Towards the Development of Floating Cities for Climate Adaptation. And I figure I'll start by giving just a brief background on the topic. So I'm sure that most of us here would be quite familiar with the challenges imposed by climate change in the 21st century going forwards. It's predicted that global sea levels may rise by up to 2 meters by the 22nd century, according to the latest IPCC reports. And by 2060, it's predicted that up to 1 billion people may be residing in these low elevation coastal areas. So those are coastal land below 10 meters in elevation. And here in the US, coastal counties account for about 40% of the population, but contribute to almost 50% of our national GDP. And therefore, in recent memory, we've seen countless kind of coastal flood hazards, storm surge flooding, for example, from various hurricanes like Katrina, Sandy, Harvey, and Irma, and many, many others, severely impacting coastal areas across the country. So naturally, engineers and architects and planners and policymakers have devised various adaptation strategies to combat climate change. So these are just a couple that may be familiar with a lot of you here in the audience. So we can simply avoid building on land that are susceptible to flooding. We can retreat, so that's relocating existing assets located in vulnerable areas, usually further inland, to protect them from flooding. Managed retreat is, of course, the main theme of this conference. We can, of course, resist or protect our assets from floods by building levees or flood walls, storm surge barriers, various kinds of hard engineering solutions. we can accommodate, so that's maintaining assets in place, but reducing their exposure to hazards. So the most common example will be elevating properties on piles or through the development of amphibious housing. And finally, we have advance. So that's actively building into hazardous areas. So in this case, we're building into the ocean, either through land reclamation or through the development of floating structures. So what's interesting is that the US Army Corps of Engineers have actually devised a whole suite of specific design measures targeting 4 of the 5 adaptation strategies. So they've got very well drawn up plans for avoid, retreat, resist, and accommodate. And the USACE kind of categorizes those solutions into non-structural, structural, and more recently, natural and nature-based features. And here's just a couple of examples there. But what's interesting is that they have not really thus far looked into the 5th adaptation strategy of advance. So again, just actively building into hazardous regions, such as the development of floating structures. So that's kind of the topic, of course, of my talk. Is all about floating cities, and the development of floating cities is actually not too it's not as unrealistic as some of you may be thinking. It's actually being recognized by the United Nations Human Settlements Program, so that's UN Habitat, and also the American Society of Civil Engineers via their recently launched Future World Vision Initiative, as a crucial step towards more sustainable and more resilient cities for, of course, climate change adaptation, in particular sea level rise. And there are, in fact, plans for the world's first floating city to be built in Busan in South Korea. So this is a collaboration between, I believe, the technology conglomerate OceanX and also UN Habitat. So here are just a couple of architectural renderings produced by OceanX for what they envision their future floating city to look like. And this is just one of many, many examples of proposed floating cities proposed for the near future. So why floating structures? Why is this topic important for us to discuss? Well, they actually offer quite substantial economic and ecological advantages over more traditional forms of land creation. So in particular, traditional land reclamation. That's when you just dump earth into harbors to create artificial land. Floating structures can be built anywhere in waters of any depth. They are, of course, inherently base isolated against earthquakes, so highly appealing for regions quite susceptible to seismic events. They can be easily expanded upon and relocated due to their mobile nature. Because they're floating, they, of course, have very little impact on the seabed ecosystem. And in fact, they can even enhance local marine activity by providing habitats for various marine organisms. And most importantly, they are, of course, immune to flooding and sea level rise. And small-scale floating structures, like what you see there on the screen as vernacular architecture, they've actually been in use for many, many centuries in locations and cultures all around the world. In particular, the Reed Islands built on Lake Titicaca in Peru. And of course, the floating fishing villages on the Mekong Delta in Vietnam. But large-scale floating structures, so as an annex, for example, to an existing coastal metropolis, they do not currently exist. And because floating cities are so unprecedented and how they represent a dramatic departure from more conventional approaches to urban development, there are many challenges that must be overcome to really facilitate their implementation and development at the community scale. So here are just a couple of examples. There's a lack of technical and legal framework to really facilitate their design and their construction. The developers are, of course, naturally risk adverse towards solutions that haven't really been trialed before in the past. And of course, the general public is quite unfamiliar usually to permanently living on a floating structure, floating on the water. So therefore, it's quite imperative that we develop an accessible communication tool and an education tool to replicate these highly complex urban environments to really support stakeholder decision making, to really educate the general public unfamiliar with these unprecedented urban solutions, so that they can make up their minds whether they feel this kind of solution would be appealing to them, or not. And this is where the idea of using immersive virtual reality comes in. The advantage of VR is, of course, we can simulate highly complex environments. Environments of really arbitrary complexity, interior and exterior environments in the context of a floating structure, for example. And because floating cities are quite susceptible to motion, so environmental vibrations due to waves or wind interacting with these structures, these vibrations can also be easily replicated inside the virtual environment itself. So therefore, it's quite an accessible tool to really engage participants and kind of to really test whether those vibrations would be acceptable for individual people from the perspective of habitability and comfort, for example. And because of its realistic nature, we can obtain very authentic human reactions to living and working inside these kinds of unprecedented environments. So to really test this concept of using VR to replicate a floating environment, we turn to a proof of concept. So the proof of concept that's based on a hypothetical floating structure. It's called the Module 9000 platform. It was first introduced in 2009 by Wang et al. And it's essentially a rectangular platform measuring 75 meters by 100 meters, and it's supporting 6 buildings. Each structure is 30 meters tall, so approximately 10 stories. And we say, okay, well, let's take this structure and place it somewhere in, say, Singapore, which is quite, which is obviously doing a lot of work in terms of floating structures right now. The water is 18 meters deep, and we basically replicated wave conditions based on 3 different wave return periods. And here for this example, we just assume that the waves are propagating along the transverse direction as shown here on the slides. So the first thing we did was to really make sure that we're accurately replicating the environmental conditions at the site. So by environmental conditions, what we mean is the wave conditions. So again, we replicated 3 different return periods: 1 year, 50-year, and 100-year waves. So here are the significant wave heights and the peak periods associated with these waves. And we can quite easily use the wave spectrums. In this case, here is just the Jones swap wave spectrum. It's fairly standard in oceanography, to kind of replicate the energy content, to describe the energy content associated with these waves across these 3 return periods. And by using just an analytical method, we can combine the wave spectra with the structural properties of our building to predict exactly how the building is going to vibrate as a function of time across various degrees of freedom. So in this case, we have vibrations for sway. So sway is moving from left to right. Heave is moving vertically, so along the z-axis, moving up and down. And roll, so theta x, that's simply rolling, moving, rotating about the center of rotation shown there. So of course, this is not meant to be a technical presentation, so I'm not going to go into too much detail about how we computed these motions, but here they are for our 3 return periods. So next we turn into the development of our VR environment. So here what we did was we took and an apartment unit that's being rendered within the Unity 3D engine. And then we've isolated a particular room within that apartment unit. So in this case, it's the living room. And then we said, okay, let's assume that this apartment unit is located on the very upper story of our building. And therefore, once we specify the location of our apartment, we can use a VR camera rig to basically replicate the internal environment of this apartment for a participant to experience. And of course, we can then translate the motions experienced by the structure about its center of rotation to the location of the room. So essentially, this room will be vibrating and oscillating in conjunction with the waves that are exciting this entire floating platform. All right, so here you should see kind of an animation of what a participant would experience when they put on the VR headset and experience this environment for themselves. I have to add that it's really quite complicated. It's quite challenging, really, to visualize a VR environment on a 2D screen. You really do have to put on the headset and experience this environment for yourself. But if you were to just put on the headset and look straight out the window, basically you'll see how the building would move relative to the exterior ocean environment. So this is a response for a 100-year storm event. So basically it's a really large storm, really large waves, and this is kind of what you would expect if you were living on a floating structure during that particular event. And of course, we can simulate all 6 degrees of freedom within VR, but because we assume that waves are only propagating along the transverse direction here, we only need to care about sway, heave, and roll degrees of freedom. Our input-output signals are synchronized using a delta time function, and basically what that means is it allows us to avoid cumulative errors due to potential frame rate fluctuations that may occur within the VR simulation. So one of the most important things about VR is the accuracy produced, or the accuracy of motion experienced by the participant. And what we've observed is that the average accuracy actually varies from around 96% to over 98% across our wave return periods. The error across the different degrees of freedom, sway, heave, and roll, are 2.4, 1.8, 3.9%. Respectively, so a very high level of accuracy in terms of its ability to replicate these kinds of environmental vibrations. The average frame rate we found was around 71 frames per second. And here is essentially a plot that's overlaying our input signals. So that's the signals that we are feeding into the VR program. And the output signals, so those are the motions physically being experienced by the participant. They're virtually entirely synchronized over the entire period of our simulation, which encompasses around 3 minutes, so 180 seconds. So a limitation to using VR, however, is the effect of a frame rate drop. So sporadically, we did observe some low frame rate occurrences, the lowest frame rate occurring at around 6.8 frames per second. Fortunately, they did not occur very often, but when they do occur, it could be quite a jarring experience for the participant, so that we have to watch out for. And in this instance, fortunately, the frame rate only occurred over approximately a 200 millisecond time frame. So a very, very short period of time where we would have these kind of sporadic drops in the frame rate. Right, so what we're showing really is that VR is a feasible tool. It's a cheap way of reproducing these highly unconventional and complex building environments to really kind of present a cost-effective way of communicating to the public what living in and kind of engaging with these floating environments would feel like, and therefore it's a highly valuable education and decision-making tool when dealing with these unprecedented infrastructure solutions for climate adaptation, for example, living on a floating city. But more research is needed on kind of various aspects of this approach. What we're working on right now is actually combining virtual reality with a physical motion platform. And that, of course, introduces a new element of motion to the participant, in this case, combining visual cues with vestibular motion as well. Of course, we have to, avoid having too many of these abrupt frame rate drops to make the overall experience much more seamless and realistic for the participant. And finally, there's really a lot more work that needs to be done, not just in this context, but in VR in general, about understanding the potential implications of cyber sickness that may be induced by VR on various populations. And with that, I'll end my talk. Thanks for your attention, and hopefully you found this informative. Thank you.
Hello. I'll ask a question about the floating cities. Could you describe a bit more about the sort of hazards that might affect floating cities and what you think would be kind of an ideal environment? I'm pulling off some of my colleagues' work in Brazil, like with looking at riverine flooding, where you have like slow moving fluvial flooding, where like 8 months of the year it might be a floating city. And I feel like that was getting me thinking about sort of this ocean environment too. Like if you have a tsunami coming through, or a lot of the Oceania kind of region sort of experiences. So thanks.
Right. So that's a really good question. So right now, this idea of floating cities is essentially a new way of thinking about land reclamation. So that's essentially having these floating modules adjacent to existing land that's sheltered from severe waves. So typically what they do is they would build maybe breakwaters to prevent these large waves from coming in and kind of interacting with these floating structures, so that you have a more or less calm environment all year round. So that's kind of the main hazard is to do with large waves from a storm surge, for example. When you have a big storm, you obviously don't want waves that kind of excite the structure excessively when you're kind of constructing a floating city. So it's usually not just the structure itself. You would have a whole suite of protective infrastructure to shield your floating modules from any kind of extreme events from waves or from wind and stuff like that.
Can I ask a question about India? I have a question about some of the attributes you might use for some of the administrative units, like such as areas that are tribal lands, because they have kind of different agricultural accommodations, and also some conflict, like that central area that is very affected by Naxalite activity.
Yeah, I'm getting a little bit distracted by can you just really briefly repeat? Yeah, so that's a very good question. Like mostly for field research, that is a very problematic area to conduct. Although, yeah, with good contacts in the field, you can still do pretty good research there. Yeah, I wouldn't know how else to answer at this point. But I would have a quick question for Cascade on the. Sorry to interrupt you, but so like talking about this hot, high, humid days, very dangerous for hard manual labor. And if you look at the globe, basically the worst areas hit are the Indo-Gangetic plains. So parts of India, parts of Pakistan. How do you look at this? Because I find it a very interesting context, especially with the work that you're doing. Yeah.
Problematically,
I think we're flying kind of blind into the future that we're going into, and we can make our high resolution data sets or better projections. But I think at the end of the day, I'll put on my social science hat, and that we have to come up with a different system of value. And capitalism is not a bad thing by any means, but we view capital in one way and not in another way. And these people who are facing the burden of climate change are disenfranchised by what we value. And we have to deal with this problem. It's just full stop. And the solutions being proposed, I don't think are necessarily tenable. So air conditioning is often brought. And I was talking to a colleague in India about and I'm not an engineer, but about the energy transfer of hot air out into streets from air conditioning units. And that when you have even structural inequality among the poorest of the poor, globally speaking, that it just trickles down over and over. And so when I look at this, I think of this as something that needs to be solved much more at like a political and cultural level, because I don't think the climate, we're not mitigating fast enough to avert these problems. The flip side of this, I think there's really, because the climate, especially in the tropics, the climate data is so challenging to work with, I think I'm not even going to say his name because I'm not a big fan. There's a New York Times columnist who had an interesting piece from last summer about why we haven't seen like mass casualty events due to heat waves. And I think that is because even on the physics side of things, the land atmosphere interactions between temperature and moisture in the tropics are just really poorly understood. And our historical data doesn't capture it. And until we really have a better understanding of that relationship between temperature and moisture, those truly extreme thresholds, I don't think, even if you put people in climate chambers, which people do, and I'm glad I don't have to do IRB for that, we don't really know. But I know there is a push against environmental determinism from its historical origins, but I still think there's very clear relationship between our environment and the way we interact, and the structures put people into that environment. And those are the structures that we need to address. Sorry, I was a little long-winded, but in short, very alarmed, not sure what to do about it.
Loving this panel discussion.
This is actually not a question, but some like suggestions to Robin in particular. There are similar studies that looks at like for example, in the Journal of Basin Studies had an article from Bangladesh in their last issue, I think, which was like again problematizing how does this huge funding comes to Bangladesh, and then how researchers from like here in America and Europe like come, and then this conceptualization of climate migration like takes place. So that might be one resource for you to like look at. And also in thinking about migration within India, migration within India has always existed actually, historically. Now, the regions that you're talking about is again, are hotspots from where people moved historically and even now. So the challenge might be this, that how do you distinguish and say that this is climate migration, or this might be X percentage factor might be out of climate, might be like one of the challenge for what you're like looking at in that sense.
Yeah, thank you for those comments. But you are echoing what I said earlier about being very critical of this literature. And indeed, we know that from Bihar and Uttar Pradesh, and also from Jharkhand, historically for let's say already 150 years, there's been a lot of labor migration, which is mostly seasonal. I'm just saying that it could very well be, but still the research is ongoing, that these labor migration flows will be exacerbated over the following decades. And anticipating that and better understanding that from both the source areas and destination areas could go a long way in sort of streamlining these flows. Because right now, we know very little about it. So even though you say, and it's true, there's a big literature on that yeah, there's a lot of migration historically from Bihar or these other areas, the exact flows, we don't know. The estimates range from 100 million to 300 million labor migrants across India. So yeah, more work to be done. That paper that you referenced on Bangladesh, yeah, please send it to me. And there's a guy up there, Jan, wake up. He's working a lot on Bangladesh. So he'd like to talk to you as well. Thank you for that.
Hi, thank you all for a really great session. Climate modeling was really new to me and I learned a lot from you guys. I just had a question about, so many of these climatic events, like it happens after a disaster has struck, right? Like floods in Pakistan, flooding in Assam, typhoon strikes. There's a huge coastline. A cyclone has come on one part, not everywhere. So what part of it is like forced migration where, my village is destroyed, my land is destroyed, I'm forced to move out of here. And maybe a neighboring village is not moving out because they're completely fine. And another part of it is how many people actually stay back to rebuild there? Not everybody wants to move out. Like a cyclone has come, struck my village, my land is gone, but I'm not willing to actually leave my land and the waters have receded. And I'm thinking it's a 1 in 100 years event, which we know it's not really 1 in 100 years anymore, but I'm willing to stay back. And then how does, how are these factors factored into your modeling systems? Are they factored in or are these just too variable?
To me, yeah. Well, let me just quickly say, so yeah, that's a great point. It's slightly different from the stuff that I'm researching on labor migration. So yeah, it featured. So when you're thinking about labor migration, there are all kinds of other dynamics at play. When you think about more forced migration and permanent migration, that's a whole nother subset of migration scholarship. So in my models, they don't feature because I really feel that what's happening along the Indo-Gangetic Plain in terms of these hot, humid days and in terms of agricultural populations, that right now is the most pertinent. I'll let you take it from there.
I just want to say that's actually a good point. The fact is we mostly focus on migration, but what it is really, it's not the same everywhere, right? If you have your land destroyed and you have no other option than to leave, that's a displacement technically. If I see my income decreasing and I calculate I won't be able to sustain the needs of my livelihood, and I make the decision maybe to try to find some other alternative employment somewhere else, this is more like a routine form of migration. I make a economic calculation. So, and the data we have, and that's a really problem we face, it's not able to disaggregate is technically very different form of migration, from displacement to migration. So in a way, it's not a good answer because I'm not really answering your question, but that's a very important issue you're raising. So. Well, I have a question for Cascade, actually.
I like this. Go for it.
No, that's really cool stuff what you've been doing with your colleagues. I mean, like downscaling is not cost-free, right? It does introduce some errors in the process. So you go from those CME5 1 degree cells down to a 30 seconds cell resolution or something. And it does lead to some errors in the estimate. Have you tried to estimate how accurate are those downscaled?
Yeah.
And I'm asking this because the goal behind chips and looking at weld bulb is to try to get better estimates for countries in the global south, West Africa, South Asia, etc. But these are already countries with, as you mentioned earlier, a few monitoring stations, and where I think from one of the graphs you showed, accuracy is already low. And the question then is how much, and I think it relates to the discussion we had last year together, but how much this is, how many errors that kind of like, you add in this process, how much this is.
It depends. I mean, we don't know what's going to happen in the future.
Yeah.
So in terms of compounding errors in the climate projections themselves, one way to do it which I was talking with a colleague earlier, is for each, I mean, you could do it for each member, end member from each CMIT-6 output and do the same process, which would produce, well, if you did it for each end member, it's 156 times 15 terabytes of data. So you could do that and you could put some bounds. The method we chose to do is to kind of, at least this is just with the CMIT-6 uncertainty between them. We decided to collapse that in on itself. So for each model, we take the end members and we take the average, and then we take the ensemble mean for each month and then calculate the historical deltas. But you're spot on. And I will be completely honest, I don't fully understand this. This is something Emily led on the paper, that we do show that if you basically start subtracting 1 degree and compare the outputs, that from the output historical runs, so they run the climate model and it's what does the history look like, that they, and this is well known, they tend to be cold. And we find the exact same thing. And so the hope is by rooting those CMIT-6 projections in a historical climatology, which is really fundamentally what we're doing, is if you look at that model of LA, it's saying, well, what is the background climate in this giant grid cell, and trying to capture that, because that helps capture the inherent chaoticness of daily weather variability in a small area. But it's a very long-winded way to say that you're exactly right, that anytime you take coarse grain data and downscale it, you're going to inherently change the fundamental system, and you're neglecting the physics in that, and also the statistical change when you do that. Does that answer your question?
Yeah.
The best of my ability.
Now it was a bit of a challenge. I was curious about
Yeah, I think, and hopefully some of this will flush through in peer review, is getting out of our own tunnel vision of how to do it better, and at least how to quantify the uncertainty of what we've produced so that people can see that more clearly.
Thank you. It's
All
over.
right, we're at time. Thank you so much, everybody. Thank you, our panelists.